It's an honor to be here in the SANER. Thank you very much. My name is Caio Barbosa. I'm a master's student of the PUC-Rio, Catholic University of Rio de Janeiro. This is my colleague, Filipe Falcão. He's a master's student at the Federal University of Alagoas in Brazil. This work was made in collaboration with the Federal University of Campina Grande, Brazil. And we're going to talk about the unrelated technical social factors in the introduction of bugs. Well, the GitHub is a coding collaboration environment that allows very much of developers to submit code, and there is plenty of information about that code. But GitHub is also a social network that allows the same developers to communicate with themselves, to submit bug reports, to ask for new features, and also to participate in code review. Since our interest is on bugs, you're going to look for commits that introduce bugs. This is an example of a commit that introduces a bug. The developer that made this commit, he touched 11 files, he added over 300 lines of code, he moved over 100 lines of code, and the aim of this developer was to make a engineering change. Those are a few characteristics of this commit. But this developer, at the moment of this commit, when you look into all the comments that he made, over 60% of his commits introduced bugs in the system. So you have a high number of developers introducing bugs, and maybe those bugs cannot be reviewed or something like that. You can see that those factors there are technical factors, but as you can see, a few days later, the same developer that made that commit, he opened an issue that was a bug report about a bug he found. But this bug was inside the code that he submitted a few days earlier. This developer, he didn't ask anyone to collaborate with this issue. He just submitted with a title, without any description, without any pull request, and asking nobody to review. He just closed it with a commit, and a few days later, other comments were made inside this issue. But if he's already closed that issue, why he committed more? Probably he didn't fix that bug. So he kept committing without any code review. Those are a few social factors that we can think about the introduction of bugs. No comments, no descriptions, no reviewers invited, or so on. That can make us think. Can technical social factors assist code reviewers to avoid the introduction of bugs? That led us to two research questions. The first one, do bug introducing comments differ from clean comments in terms of technical and social factors? How strong or relevant is that difference? And the Ricky 2, in the presence of multiple factors, what factors most affect this bugginess of a commit? To answer that question, we have the two factors that we are looking, the technical factors and social factors. Such as technical factors, you can see the not most common ones have to follow technical contribution norms. It's like committing with small files, few changes to facilitate the code reviewer. The nature of these commits, if it's a engineering maintenance ones, and the project establishment, that we're going to see the age of the repository to see if it is very established in the community. And the social factors, we have the social influence on contributions, that if I make a comment and I'm very known in the community, this commit will be very good review. The people reviewing, you look to me as an experienced developer, they will make you comments saying my code is bad, or you're an experienced commit, so you can just accept that request or something like that. Okay, those are a few metrics that compose our factors. You have 14 technical metrics, and 80, I think it's 8, social metrics. Those are the ones that are used in our study to measure those probability of a commit is buggy.
Okay, so to perform our study, we selected manually 8 GitHub Java projects according to the following criteria. The projects must be relevant, they must be active and active for a long period of time, and they must use the issue and pull request GitHub system so we can standardize our analysis. So our approach consisted on 5 steps. The first one is to mine the repositories of the projects we selected, and in this mining process we extracted the commits, the pull requests, the comments, the developers, and the issues. The second step was to extract the bug reports. By the issues that we collected, we can check which ones are bug reports through their label, such as bug or defect. The third step was to find the bug introducing changes. From these bugs, we use the SZZ technique, which allows us to state if our commit is clean or buggy, if it introduces a bug or not. Then we compute the metrics for all of the commits on the projects, the clean ones that never introduced the bug and the ones that introduced the bug, and then we perform our analysis. So this process resulted in a dataset with almost 100,000 commits, with almost 3,000 developers, and more than 10,000 bug introducing changes. So on our results for the first research question, we use the Wilcoxon-Rank-Sum test to test if there is a statistically relevant difference between 2 populations. The populations are the values of a metric for the buggy or the clean commits, and we use the Cliffs Delta test to show how strong is that difference. In the table, the ones that are the cells marked are the ones that were statistically significant, and the ones that have a plus sign are the ones where the Cliffs Delta was positive, so there's a positive relation between commit bugginess and that metric. The ones with the minus signs, there's a negative relation, and the asterisks are for how strong is that difference according to the Cliffs Delta. When there are no asterisks, because it's a negligible effect, 1 means a small effect, and 2 means a medium effect, and finally 3 means a large effect. So our results show for the first research question that the technical factors were statistically significant in 71% of the cases, while the social ones were statistically significant in 17% of the cases. We can also see that the technical factors, the technical norms factor was statistically significant in 82% of the cases, and that the change lines metric, the modified files, the buggy commits, that's factor 4, and the age metric factor 5 obtained statistical significance in all the projects we analyzed. Moreover, the buggy commits have statistically significant higher changed lines, modified files, and the percentage of buggy commits values. We also see that values from the social influence factor are significantly lower for just 3 projects, the Elasticsearch, the Spring Boot, and the Signal Android projects. So we can conclude that both the technical and social factors are able to discriminate between buggy and clean commits. However, we can see that the technical factors were more determining than the social ones. Now on our second research question, we used multiple logistic regression analysis. We built a model for each one of the projects studied, and we used an odds ratio analysis to check the effect of the metrics in the model. An odds ratio bigger than 1 means a positive relation with commit bugginess, so there's a risk increasing effect. And the odds ratio smaller than 1 means a negative relation, what we call a risk decreasing effect. Like the previous results, the cells in gray are also the statistical significance results. And we can see that some metrics are absent in this table. The reason was that many metrics were removed from the models due to multicollinearity, that we needed to remove them to secure the stability of the model. So first, on the risk increasing effects, we see that the changed lines obtained a risk increasing effect in all the projects that we studied. Still on this metric, we see that it reached the highest effect in 7 out of the 8 projects, and it also reached the highest effect of all the effects analyzed on the Spring project. Moreover, the percentage of buggy commits, the modified files, and the percentage of tests in the developer's commit also presented a risk increasing effect, but only on the 4 projects only in 4 of the projects we analyzed. So now the risk decreasing effect, we see that the age metric from the factor 5 project establishment presented a risk decreasing effect in 4 out of the 6 projects where it was statistically significant. The commit ownership, the factor 6, also obtained a significantly risk decreasing effect in 4 of the 6 projects where it was statistically significant. And the social influence factor, the last one, presented a risk increasing effect in 4 of the 5 projects in which it was significant, although those metrics were highly removed due to multicollinearity. So, after presenting the results of our analysis, we present some discussions that we found could be interesting. The first one are the contradictory effects of the experience metrics. The Spring Boot and the Signal Android projects showed a negative effect for these metrics, so they were negatively related to commit bugginess, while the NET and the Hack Java projects showed a positive effect. So, to try to clarify these contradictory results, we analyzed the correlation of these metrics with the complexity of the changes to try to see if there's a relation. And we found that in the Spring Boot and the Signal Android projects, there was a negative relation between the experience of the developer and the changes that he performed. So in these projects, the more experienced the developer was, the less complex the changes he was proposing. This was related to the nature of the projects that were becoming very big projects. So the developers that were more experienced were doing very documentation and administrative tasks. While in the NERI and the Hack Java projects, we found a positive relation of the experience and the developer and the complexity of the changes. So the more experienced a developer was in these projects, the more complex their changes were. So we cannot state causality because it was just a correlation analysis, but there are some indication that the actual effect was due to the complexity of the changes, and this correlation must be further analyzed in future research. So the other interesting thing that we found to discuss was the risk increasing effect of the test percentage metric. This metric presented a risk increasing tendency in 4 of the 5 projects that were statistically significant. And that was a little bit strange because code reviewers usually prefer contributions with tests. And this leads us to a question, okay, are tests harmful? This doesn't make much sense. So we performed again another correlation analysis between the test and the complexity, and it shows that for 3 of that 4 projects that presented a risk increasing tendency, there was a positive relation between the complexity and the amount of tests the developer performed. So the more complex changes, the more tested they were. So the actual effect was most likely due to complexity. It must be further analyzed also. But we found a negative relation in the NERI project. So again, we cannot state causality, but there are some results that we need to test in future work. So our work studied the effects of the technical and social factors on commit bugginess. We found that both the technical and social factors are able to discriminate between the buggy and clean commits. However, the technical ones are more determining. We also found that the technical factors and the commit bugginess of a developer are factors related to the increase of risk when performing changes, and that the commit ownership of the developer, the project establishment, and the social influence were factors that were risk decreasing. As implications, this work can be used as baseline for future research in the area, and this work can also be used, the knowledge we generated can be used in future tools for code reviewers to check if the contributions of the developer should be more carefully assessed, to check if there is a bug in there, if he presents factors that are related to bugs. So that was our work. We appreciate the opportunity, and thank you.
First remark about your risk reducing factors, be careful. If you say it's a clean commit, you're not really certain that there's no bug inside of it. It's just that there's no reported bug inside of it.
Yes.
Okay, so yes, that's totally true. Since we analyzed all the commits of a project, for example, if we analyze a commit in a given period of time, and it may become a bug later, you may find out actually that it was a bug. Since we covered all commits for the older ones, we probably found if he would become a commit after, but the most recent ones, yes, that's true. We probably missed if they were actually clean or not.
So in that sense, did you try to apply the criteria for the risk inducing bugs on the known risks to see whether there's actually some kind of predictive power inside of it?
We don't try to predict if it was buggy or not yet, but future work that we tend to access.
And then, can you explain a bit better this test percentage? How did you calculate that?
Okay, that test percentage was the amount of times the developer tested his own code. So, like, he made 10 commits and he tested only 5 of the code he made. So it's 50%. That's
so is there some coverage information between the test and the
we had a test coverage metric, but that one was removed in multicollinearity. The test percentage permanent.
Because there may be an explanation for what you see.
Yeah, maybe.
Developers write tests for the risky code.
Yeah.
And so that might be an explanation why.
Probably the tests are not very good, but yeah.
Yes, the risky code, it's most likely the complex code that we saw in the discussion, that relation. So yeah.
Maybe I have even a question for search, but maybe it's for the whole group. I mean, both for the first and the third speaker, you raised the issue of, okay, how do you know that something is buggy or not? So how do we actually see that empirical research on things like related to bugs? I mean, what would be a fair notion of how we determine what is a bug? Do you have ideas about that? Or also just raising the question?
No, but you should be careful. If you say it's a bug-inducing commit, you're certain that it's bug-inducing. But that doesn't mean that the opposite is true.
No, so I agree on that. I'm just wondering, and maybe people have ideas about that. So what would be a valid approach? Maybe you have.
Yeah, yes, we have the information now that that commit is bugged, but in the future that information may change. But we can do research in the information that we have for now. That's the unfortunate fact. I agree with you.
The point is that, okay, we should be more careful stating if a commit is clean or not, because we don't know for sure. It may not be. But yes, we may like lower down the bar of our findings, say, okay, be careful. We know now that they are clean, but they may not be. So that's definitely a threat to validity. But we are working now with the SEZ approach to determine if a commit is clean or buggy. That's what we have now, the state of the art. The software engineering community is definitely doing work on that approach to improve its performance. But yes, that's true.
Sadly enough, there's no easy answer. There's no easy answer.
Well, I was convinced about that part. But I thought maybe someone has a very cool idea to help the community here. I also don't have a clear answer there. It looks like it's a hot issue. For this type of research, and in this session we have 2 papers.
Any other questions? Okay, thank you very much.